Today's lecture is actually something of a novel implementation, a unique implementation of production flow analysis. You've already been told that, or you already know that production flow analysis is a comprehensive approach to implementing or achieving flow throughout an enterprise. So Burbidge applied it to the supply chain, but initially when he began talking about and writing up about his method, he had 4 stages. Factory flow analysis, where you look at the flows of products across major shops or buildings. Then after factory flow analysis, the second stage, the drill down, was called group analysis. This was where you looked inside each building, typically a machine shop or a forge shop or a sheet metal shop or a machine shop, and you tried to organize the layout into manufacturing cells. That was group analysis. Third stage of production flow analysis is line analysis. This is where you look at each individual manufacturing cell and you try to improve the layout and ergonomics and safety and scheduling internal to each cell. And then the final stage that Burbidge talked about was tooling analysis. Now in his books, he talked more about grouping parts with common setup requirements, common tooling requirements. So in many ways, what Burbidge said and called tooling analysis, Shigeo Shingo, the godfather of single-minute exchange of dies cell production, kind of said in the same way, but I think that Shigeo, being the great industrial engineer and mechanical engineer that he was and continues to be in everybody's eyes, he gave a far more detailed insight into Burbidge's stage of tooling analysis. So today's lecture is essentially our applying production flow analysis and the principles of tooling analysis in combination with industrial engineering methods analysis to a problem. A problem was of reducing changeover time on a forging press in a tier 1 forging supplier to the automotive industry. But what we did was we kind of looked beyond just the facility layout aspects of FAST, and we also looked at an extremely important component of the production system, that is activity scheduling. So you'll notice the title is basically methods analysis. How do you look at work being done at a particular work center or set up intensive equipment like a forging press, and then how do you apply flow analysis at that level? In this case, we looked at the flow of the operator moving around the equipment, and we said how could the workplace layout be designed in such a way that the total amount of non-value added time that the operator spends during a work sequence that constitutes a setup, how can that total time be reduced? But we also found that if we put on the hat of the industrial engineer, that work is not just about eliminating waste, it is also about ergonomics, it is about safety, it is about standardization, but a big component of work improvement is scheduling. Typically, Lean, having come from assembly, tends to look at all work as being sequential linear, and they look at all work being decomposed into an assembly line-like structure. I think that is fundamentally incorrect. There are many work patterns which resemble job shops. In fact, many work patterns which look like projects. And one of the highlights of work that is structured as a project is that there are multiple activities that could be done in parallel. So in this presentation, we are basically going to tell you about an application of work that we are doing in a current project called SmartChart. So our first project, which had been funded by the Defense Logistics Agency, was JobShop Lean. We created FAST, the software from that. Now what we're doing is we are looking at reinventing the core, the foundations of industrial engineering, work design, methods analysis, time studies, and try to apply that with some more advanced scheduling methods, computer methods, to how we could look at setup as a work process and improve things. So our agenda is pretty big, but don't worry, I'm not going to keep talking till the cows come home. Let me first give you an initial understanding of the problem that we focused on. So you've probably heard about setup production. And setup time essentially is the time when the equipment stops producing the last part in the batch for a particular order, and the total time it takes for the time when the same equipment starts to produce the first good part of the next order. So typically setup time can be broken into the time it takes to tear down the existing setup, the time it takes to prepare for the next setup, and then the time it takes to actually perform the detailed setup for the next order to be worked upon. So that is typically the total setup time. And then of course we can look at those activities which have to be done, we call them internal activities, and then we look at non-value adding activities, and appropriately we can look at setup time as having its own value stream, and then we can compute a value added ratio even for setup, meaning that the total setup cycle, there's so much time which absolutely is time that you have to spend in setup, divided by the total time it took to perform the setup, and the more that ratio hits 1, the better that you are at quick changeover. So, thinking as an industrial engineer, when you look at setup time, and we look at setup as a process, as an industrial engineer, the first thing which you do is you try to break it down into elements. So here are examples of some of those individual activity elements that constitute the tear down sub-process, which is part of the overall setup process. So like loosening bolts, removal of the previous die, then how do you prepare for the new setup? So you gather the items, you clean the area, you clean the table, you exchange the die racks. The die rack for the previous die gets pushed back, and the die rack for the next die is brought in, and then actually you start the setup for the next order. So you load the new dies, you insert the bolts, and then you make adjustments. So this is basically the first thing in any kind of process improvement activity. So even tooling analysis, the fourth stage in Burbage's powerful method of production flow analysis, this is what you would essentially do. You look at the elements of setup of the equipment, and then you try to associate those elements with design features, tooling features of the various parts which will be run on that particular machine. So what was the general strategy that we feel as a good bringing together of Shigeo's brilliance and what we also understand to be classical, powerful industrial engineering thinking? So the first thing is industrial engineering. Industrial engineering is founded on the whole principle of work improvement, that you can design work and you can improve work, but then fundamentally how do you do that? You take work, you decompose that into processes. These processes will have elements, activity elements. You look at individual elements and say, can I eliminate them? Can I combine them? Can I change the sequence in which they get done? Are certain steps taking too much time? Is there imbalance? Can I maybe have the same step be done by two people or be done on two different equipments? It is called parallel work. And then finally, having gone through this rationalization and raising, only then you try to automate the work. So even Bill Gates said that the worst thing you can do is try to automate and computerize a bad process. So our strategy for tooling analysis as applied to setup production would essentially be to take industrial engineering and then combine that with Shigeo's brilliance, which is his setup production process. And at that time, since he had begun by applying that to reducing die changeover on presses, he called that single minute exchange of dies. And so a very powerful thought process that he came up with was, you look at the activities being performed and you try to separate them into both internal operations, that is, the machine has to be idle for those activities to be done, and then as much as you can, take the work off the machine so that even as the machine is in operation on the previous order, you could be performing these setup activities in parallel, preparing the machine for the next operative. Second thing is again, parallel activities. There's so much that needs to be done, and sometimes experience matters, and sometimes maybe just by representing the work in a different way, you identify opportunities for performing work in parallel. Okay, and of course, once you know that work has to be done, if it's burdensome, risky, if it's slow, then you try to speed up the work. So again, setup production, tooling analysis, this is where, powerful best practices like standard work, safety engineering, physical ergonomics, direct time study, teamwork with the operators, all of those things really come together in a wonderful way. So what we essentially did was we integrated both industrial engineering and whatever little we knew about setup production. So, we did time studies, we created the classical flow process chart. This was something different. What we did was, once we had the activity decomposition of the setup process, we looked at the various activities and we said, can certain activities be done immediately, or do certain activities require other previous activities, predecessors? Then spaghetti diagram captured the flow of the operator, the flow of the tooling. The Gantt chart is the visualization of the work schedule. Again, this is another unique element of our smart chart method, that we leveraged modern day industrial engineering best practices and thinking processes too. This is standard work again, visualization, cleanliness of the workplace is most important. How much of the work area can be visually managed? This was also something which we felt was important, that this company had a pretty good ERP system, and what we felt was that it was also important that besides raising and streamlining the setup process, that there was a scheduling element which signaled to the die prep shop, thou should be ready to prepare dies, as well as to the press operator, you should be expecting this die to have arrived and be ready for setup on the press. And then of course, you cannot do setup production in isolation. Setup production has to be done in the context of the bigger picture, which is, let us schedule the orders that we need to schedule so that they can be finished by desired due dates. Given the company being a German company, we had a lot of good data, and so what they have is, they have a MES, a manufacturing execution system, which is able to keep a very good time log of the critical equipment in a forge shop, which is basically the presses. So you can see that for each period of operation, they were able to give us the breakdown of various activities, elements or categories that they felt were necessary but not value adding, and easily non-value adding. So this is how powerful automation is, in that it is able to keep a log of the various categories of utilization of good or bad of equipment, and then against statistical analysis of that utilization, you can see, for example, here that these are all the categories of failures, where the machine was basically losing capacity, either being idle or just doing work which was considered non-value adding. Now this would be wonderful data that a Six Sigma project could be built upon, but again, it is not necessary that we call setup production a lean project or an IE project or a Six Sigma project. I'm just an industrial engineer, and I'll just make whatever improvements are necessary. But you can see that this was the data that we began with as a basis for justifying that this project, where we were going to apply fast and scheduling algorithms to work improvement, has an impact on the bottom line. And the bottom line was, if we can make available, we can free up existing capacity on the press, then despite having to do more setups, they could run a variety of orders, and thereby they could ship more parts to customers, and that's effectively how setup production would impact fiscal gains. This is just a visualization. It's the same data. This is by period and this is by category, and you can see that this profile and the trends are what essentially guide you to say, yes, setup production was a worthy application of smart chart and the whole thinking process underlying smart chart when we undertake process improvement and work system design. Next part of the agenda, I will give you a brief overview of Hirschvogel, give you an overview of this whole idea of smart chart. That's the current project being funded by Defense Logistics Agency, and then share with you some of the project goals and objectives. So this is some information about Hirschvogel. They were a great partner for us on this particular project, and they pretty much supply all the brand name German automotive makers, but they also supply Japanese and US car makers. They're just about 15 minutes drive from the Ohio State campus. So they have these forging lines, and we worked on certain machines, and they also have fully automated precision machining machine shop, because they make high precision components for various automotive customers. So what is Smart Chart? The idea of Smart Chart is that when we look at a process, when we look at, say, an entire system that does some work, or we look at one process that's very crucial to the performance of that system, we as industrial engineers have been taught for decades that there are some fundamental charts that allow us to document the work being done in the system, or just document the one process, and then to step back and against what each chart tells us to make certain conclusions about where the improvements should be made. So, for example, the outline flow process chart, this example is just for coffee making. You don't make too much money selling coffee, but the outline flow process chart is typically something which would result even from a Gemba walk, where you walk into the workplace, you observe the work being done, and then you draw some conclusions and chart the process. So circles represent value-adding steps and squares represent inspections. These are classical industrial engineering mapping tools. Then, since the person making the coffee is a key player in this particular system, we develop what is called a person type flow process chart. So we look at the exact sequence of steps they perform, how much time they take, where they do the work, and then the type of the activity. Is it transportation, waiting, inspection, value-adding work, or is this person putting work into inventory? This is called a spaghetti diagram. It gives you a spatial representation of the person type flow process chart. This is the MRP bill of material. This is basically telling you how the product gets put into shape. The big thing which is missing in most industrial engineering charting methods, especially in the lean tools literature, is the Gantt chart. And I think that is because scheduling is the hardest, and so typically by assuming that all work is assembly, which is basically requiring first in first out scheduling, most practitioners have ignored the value and the need for good scheduling. So the idea of Smart Chart is that each of these charts tells me something about what is wrong with the process and what could be done to improve it. Then by using different combinations of these charts, I'm able to home in on, say, the constraint activity. This is theory of constraints talking. But it's the schedule that pretty much drives what matters most. If we are looking at timely delivery of work and we are looking at cash flow, the time it takes for money to flow, then we need to look at the schedule, the current and the proposed schedule after improvements, as the guiding light when we look at process improvement. So the Smart Chart Process Planner, what we have done, for example, is we took the Toast Kaizen video that is published by the Greater Boston Manufacturing Partnership, and we tried to show that the creators of that particular resource, while they did a good job, they missed so much that industrial engineers could easily add. And as a result of that, now what we have is we have that particular video, and we offer a 15-page instruction manual which tries to show how all these charts, when they complement the basic observe and improve policy and strategy of lean, put together, the industrial engineer who does lean thinking, what you get is a far better approach and far better gains. So that's what Smart Chart is basically saying, that can charts make us smart, and can charts make each other smart? That means could one chart make the other smart, enrich its diagnostics? So while the human being is involved, what we have been able to do is create some thumb rules on how to read certain charts, and then we have also developed or used commercial software to implement the diagnosis of various charts. So these are the project goals and objectives that were set for us, that we arrived at in discussion with the Hirschvogel team. And their thing basically was reduce die change over time using this methodology. And of course, because we were doing a pilot their thing was, why don't you first focus on these two presses? So one of them was manual, the other one was pretty much the same equipment but with a robotic loading device. The objectives are pretty straightforward: reduce or eliminate non-value added time, and basically increase the savings. And of course, give them quick changeover whereby they might be able to respond to smaller volumes of orders and maybe a higher mix of orders without having to pay overtime or buy extra equipment. So here's this chart will be available to you. I don't wish to go into the finer details. In fact, if you go online, my graduate student's thesis, Sachin Shah, his thesis is available online, so you could pretty much access his entire thesis, and this whole logic of how to think when we pursue a process improvement activity, like in this case tooling analysis, seller production. How do we make a process flexible? How do we make a process capable of a high mix of work? We built a thought process, and this is what we teach our students. This is what we execute. It's pretty straightforward that when you look at the classical industrial engineering charts, typically we look at work and we break up the various activities at least into 5 activities: operation, transport, delay, inventory, and inspection. In some cases we have decision. Of all these 5 activities, typically we would say, you know what, operations we can assume to be value adding. Inspections we can say either are value adding or necessary but not value adding. So the moment you look at a bunch of charts which describe a system or a process, the first thing which you start asking is, where can I eliminate the inventory points, where can I reduce the delays, and where can I eliminate or reduce the transportation. So that's what this process really is saying, that once you've mapped the system, once you've observed the system, the first 3 things you should do is try to attack the transportation elements, try to attack the queuing elements, the queuing delays, and try to attack the unnecessary inventory points. Of course, if you look at what Ono and Goldratt advise us, what they say is, don't forget the fact that work needs to be done. But even there, the operations and inspections could be necessary but not value adding, or they could be long cycle. So try to eliminate imbalance in the workflow processes, try to maybe even eliminate operations and inspections. So it's not that all work when recorded as operations and inspections is necessary value adding. So this is what the thought process really teaches all our students, and this is what we do. First, go after those obvious opportunities for cutting out waste and time delays in the overall process. So data collection, this is again this is the tedious part, and at that time we did not have access to time study software. Only today we know that there's at least a workplace planner from ProPlanner Inc., and there is a Timer Pro from Applied Computer Services, and then there are other commercial vendors of both process videotaping, and then from the videotape you can go to quick decomposition of the process into elements. So this is video aided direct time study. Sachin essentially went, videotaped the entire setup, and then it took him an entire weekend, but by playing, backing, forward, reverse, he essentially created this minute by minute, second by second decomposition of the total setup process. Of course, there were like major categories. So he sat down with the press operator, and they arrived at some major categories of activities that could essentially be bunched together. But even then, like it or not, this is what standard work is about, this is what Gemba walks are about, this is what leveraging the experience of the operator is about. That as an industrial engineer, you can go in there, videotape the person, and then flip out some predetermined time standards and tell them, hey, you're not working fast enough, etc., etc. It doesn't matter. Eventually, the beauty is that if you record the work being done in the Gemba, and there is a teamed approach to process improvement, that video is gold, because after some time the operator will be encouraged and motivated to say, you know what, I think I know where I'm being inefficient or where I'm creating scrap. So like it or not, this is the burdensome part of the tooling analysis phase of a setup production process, especially where you're looking at short cycle work and saying what can be done to eliminate non-value adding steps, to reduce necessary but not value adding steps. Now, so this is one of the key process charts that we need, and I'll show you how we use this to create essentially a routing for the operator's movement path. So all these steps, every step was being done at some location in the workspace. So every time the operator moved between two consecutive locations, that created a travel, and that became a routing. And then once you have a routing of some work being done, you can essentially run it through the production flow analysis software and make some improvements in the workplace layout. So when you break down the setup process, these are all the individual activities that get done. So all that you're doing is you're recording the sequence in which they get done, and then you're looking at the total time it took to perform the activity, any reasons why the activity had to be repeated, how much was the changeover time to prepare for the activity. But this is basically something which I think Sachin really in teaming with the operator was able to document. So enter old job data, adjust the weight sorter, adjust the robotic arm computer. These were all the major activity elements of the overall setup process. So after all that data was obtained, he basically went through the various types of activities, and he had already classified them as operation steps. We need to perform these steps. Transportation between points, inspection activities, and of course delays. So this was like a quick histogram. If you are a Six Sigma person, you might see this as essentially being a Pareto analysis that looks at the major categories of time that constitute the overall setup process, the tool changeover process, and then you take some action about what needs to be done to improve the setup cycle. So then this is the more detailed breakdown. So this is now more detailed analysis, and again depending on where you apply tooling analysis, depending on where you apply direct time study, these appropriate categories of major activities will be obvious. The big thing is that you need to have this data, because it is only when you have these time values for key operation steps in the current state process, and then you record in the future state, the proposed process, the same time elements, you can do a nice non-parametric comparison of the two states, and then come back and see if the improvements you made have a significant impact on the total change over time. So you need this data, and it took a considerable amount of time for my graduate student Sachin to get this information. But the thing was that against this information, we could then go ahead and pursue some of the computer-aided problem-solving methodologies. So here's a Gantt chart. So again, if you look at these are the activity elements, and for those of you familiar with Microsoft Project, what we did was we took the activity process and we essentially converted that into a Gantt chart. So this is what the Gantt chart would look like, and you can see again that everywhere it's just one person. So by looking at work as a project and not as a sequential process, that was one of the big mindset changes that we essentially risked. We said, you know what, can we look at setup as a parallel process and not a sequential process? So these Gantt charts, while you may or may not wish to use Microsoft Project to visualize work, our contention is that when these Gantt charts are produced, that they give operators and machine builders a visual impact on, wow, the way I've designed the work, the way the equipment is working, the way that the die and the product had to be made, there seem to be delays in the overall process. So we feel that the Gantt chart is an important industrial engineering tool that should be included in the typical lean tools like standard work instruction or setup worksheets, and that enriches the thought process and the problem solving process in something like setup production or tooling analysis. So let me now switch gears a little bit. A big thing about our project, the Smart Chart project, is that can we use computer methods not only to analyze data, not only to analyze processes, but to suggest to us automatically the potential for improvement. Now, scheduling tends to be a very hard problem. You cannot say I will optimally solve the scheduling problem. But once work or a system is represented in a way that allows it to be scheduled by the computer, there's an opportunity for the computer to suggest to us how the execution schedule of all the steps in the activity, the process, could essentially be improved. So again, first thing which you should know is that typically when you see a flow process chart which has all the activities, that this is how you are advised to look at various activities, and then these are the questions which you ask. Now, in the context of the operator movement, we are looking at transportations. So if you look at these questions, when you look at transportation activities in an overall process, can you reduce the number of steps? That's the first question you ask. Can you reduce the number of steps? Then you ask, can you combine some steps? That's a second way in which you reduce transportation time. And then, of course, can you change the layout? And this is where I would like to show that, there are computational tools available, especially the FAST software and the STORM software, where you can look at one or more processes, reduce them into a form of data that these two packages for layout design operate on, and voila, what you get is tooling analysis. Part of the improvement of tooling analysis could be viewed as a layout problem, and if it's a layout problem, then these two software tools are extremely helpful for looking at how the layout of the workplace could have been changed. So let's go back again. This was the flow process chart. This is essentially where we began. So we had to take this particular flow process chart and convert that into a routing. And the routing essentially captured all the transportations that the operator went through, moving from point 1 to point 2 to point 3 as they executed this overall setup process. So that's all we're doing with tooling analysis, is we are saying part of the changeover time involves a lot of non-value added work being done by the operator that keeps the press from quickly being changed over. So can we, by converting the operator's motion into suitable data for FAST, can we then use FAST and do some improvements that involve the workplace layout? So how did we do the operator motion analysis? This was the workflow. This was the decomposition of the total setup process into elements. So we took each step and we said, where is this step being performed in the overall workspace? So around the workstation, when we observe the video over and over again, we determined that there are all these individual unique locations around the press area that the operator is going to one or more times, right? So from a layout perspective, this is basically telling me all the points in the workspace that need to be arranged around the press. And what this sequence is telling me is, step by step, am I moving between any 2 points in the workspace? So effectively what we're doing is, with this analysis, we are creating the routing that is needed by FAST, and already we have all the work centers. These are all the locations in the workspace where that process is going to touch. So pretty much we are ready at this point to see what we can do using the FAST and the STORM software packages. So now this is just again a little handout which I've created. I'll of course go back and show you the Excel spreadsheet version also, but forgive me for the fine print. What you're seeing here is the sequence number. This is the sequence number here. So steps 1, 2, 3, 4. This is the sequence in which the various steps are being performed. So steps 1 through 51, then steps 52 through 103, then steps 104 through this. So essentially think about this as being the first 51 steps, and then with each step the location in the workspace is being recorded. So step 1 was done at location 1 in the workspace, step 2 was done at location 16. So clearly the operator had to move from location 1 to location 16. So step by step between every 2 consecutive operations, you can see that either the operation was done at this previous location or it was done at another location. So this effectively is your route sheet. Let me at this point exit to so let me show you here the input file. So work center. Since we are using FAST now for the 4th stage of tooling analysis, it's not that the routings are touching machines, it's now that the routings are basically touching work points. So it doesn't matter that this is a work center number. All we are saying is that in this column here, these are all the work points around the machine, the press, that the person was seen to be visiting to do some various activities. So with each step, you are associated a particular object in the workspace. So work center 1 is actually the press table. This is where the person really is doing most of the work. Work center 2 is the feeder hopper computer. Sometime during the process of setup, the operator was seen to go and work or do something at the computer. Then step 3 is the weight sorter. So all we are doing here is we are essentially creating or describing all the work points that the setup process had the operator work around or work visit, correct? So this is tooling analysis. We're applying production flow analysis now to design the layout of the individual workstation. This is trivial, okay? So really we have only one part number. Now, if we had been able to videotape multiple setups involving different dies, then this file would have carried many more part numbers. Here, just to make fast run, we've essentially created 2 part numbers. What really matters is the first part number. So you can see that the part number is 1, and what is moving is the operator. So really the thing that is moving, that is being tracked, for which we have a routing, is the operator. This row is just a dummy. And again, quantity and revenue don't matter. It really doesn't matter. All that we're doing is we're using FAST to produce a from-to chart for the operator's movement path. This is what is something which I had shown in the PDF file, but it will become more clear now. So here, 3 columns. This is the standard routing spreadsheet in the FAST input file. FAST has 3 spreadsheets: the routing spreadsheet, the part spreadsheet, and the work center spreadsheet. So for the first operation in the setup process, he or she visits location 1. And you can see again the part number is just 1 because it's just the operator being tracked. For the second step, goes to location 16. For the third step, location 8. Fourth step, 7. So you see, from 1 to 2, there's one trip made between locations 1 and 16. Then from 2 to 3, there is one move from location 16 to 8. This is how essentially it continues. So if you keep going down, further, step number 57 is done at location 4 in the workspace. Keep going down. So many steps are performed, and thanks to the video recording and going over it one by multiple times, this is really what makes direct time study and cell production sometimes cumbersome, but that's what is very core to the identity of the industrial engineer. And I think engaging the workforce with this videotape and having a bi-directional conversation is so much superior to the classical industrial engineering approach of, hey, my videotape shows you are wasting your time, start getting busy doing work. So I think I like what Lean and Toyota have to teach us industrial engineers. Anyway, continuing further, more steps. We are right now to the 128th step is done at location 6. The previous step was done at location 1. Continue further. I mean, look at this. I mean, we are now to the 227th step. Pretty much 236 activities were recorded for one setup. Just, it should look like, wow, it looks pretty big, right? Anyway, so this is the input data, okay? So you have your operator's movement path captured as a routing in FAST. Why? We're trying to fool FAST into doing tooling analysis, not factory floor analysis, not group analysis, not line analysis, but tooling analysis. And again, FAST is basically a very flexible suite of algorithms. There's only one operator being tracked, and these are all the various work points that he works with. There are about 21 individual working points. So you run this input file into FAST, and again, because there's only one routing, you will notice that I have only 3 outputs. So when I ran FAST, I X'd out many of the standard outputs. Otherwise, I would have got an error message because FAST would have said, you haven't given me data to do PR1, you haven't given me data to do PQ analysis or PQS analysis. So because in tooling analysis, you see this routing here? It's pretty straightforward. It's just one single routing. So because you have only one routing, all that you really care about is the from to chart, right? And so therefore over here you notice this is the Q type from to chart. Why? Because Q is essentially quantity. There's no revenue. Effectively the Q and the frequency type from to chart would give the same values. So here, this is the number of times. He moved 4 times from location 11 to location 1. Then he moved 15 times from location 1 to location 8. He moved 18 times from location 7 to location 1. So this is what is called the classical from to chart. So the rows 11, 14, 15, these represent all the locations in the workspace, and the same locations are listed across the top in the columns. So any cell in this from to chart is telling you that from the location in the row, in this case 1, to the location in the column, which is location 12, the operator moved only once. So the from to chart is a very good analysis, a data tool that can be applied to setup production and or tooling analysis. And one of the improvements that you could make is to say, can the layout of the workstation be improved so that the operator spends less time accessing various support objects? You know, there are other important aspects of tooling analysis that setup production teaches us. You know, things like ergonomics, machine controls, visual devices, poker yoke, error proofing, ergonomics. FAST is not able to do all of that. So I do not wish to say that FAST is like a silver bullet for all the problems. All that we're trying to demonstrate here is that in the job shop that is going to make a variety of parts, when you drill down to the individual constraint work centers and you look at things like setup production, part of the setup time improvements will be through layout changes. You can also use FAST to look at different dies or parts and try and create either tooling families or die groups. Again, these are different applications of the same algorithms. Here, all I'm trying to do is focus on the layout of the workplace. So this is your from to chart, and then this is the visualization. So all that you've been given here, there's not a layout of the workplace. FAST can't do this. Storm can do this. Spiral can do this. VIP PlanOpt can do that. All that FAST is doing is, it is simply helping you to visualize heavy traffic between various locations around the press area. So between locations 1 and 8, locations 1 and 7, 1 and 16, 1 and 9, you can see very quickly that there are certain locations that are strongly connected. So naturally, from an ergonomics point of view, you would, 1, want to put those locations next to each other, and 2, you would like to put them in the favored, the comfort zone of the operator. That is, if they are right-handed, you would like those zones to be on the right side of their body. If they're left-handed, you would like those zones to be on the left. What you don't want is that the heavily utilized locations where the person stands and the other locations, you don't want those locations to be behind, because then the torso will experience a lot of wrenching. So this is basically what FAST spits up. So now what do we do with that? Let's go back here. So here what you see is that this is the from to chart. This is the from to chart. So classic from to chart that came out of FAST. This is the visualization. This is where FAST starts being useful. This is where now we kick into using the other package, STORM, $75. It's a humble operations research package. I find it very useful to utilize the layout design module inside of STORM. But again, I think that if you invested $1,000, you could get Spiral, Professor Huschalk software. There's also VIP Planart. You have to decide, when you buy the package, how many applications you will have of that package and who is it who's going to get trained in the use of the package, because the rule of garbage in, garbage out applies. You might buy the wrong software. A classic example is ERP. MRP can't sketch, right? So you buy the software, it doesn't do what it's supposed to do, and then you have people who aren't IT savvy, who don't have industrial engineering background, and then you let them do production and inventory control. So just as ERP is bringing down a lot of companies and burdening them with gobs of inventory waste, so also layout design software. You do not wish to buy software that you do not know how to use or aren't comfortable with the assumptions underlying that software. So this is where FAST essentially starts being useful. This from to chart and these locations which you see of the various work points, we put that into the STORM package. So if you look at the STORM package, what we did was, we said, look, if this is where the press is, this is the sweet spot, this is where the person stands in front of the press, then we would like to keep as much as possible all these work points in a circle, right? Because the circle is the logical way to have the person at the same distance from various points. So again, we had to fool STORM into doing some of the things we wanted it to do. So in STORM what we did was, you see these locations called dummy. This is basically telling STORM that I would like you not to put the various points of work in these locations. Okay, so this zone, by the way, this is my graduate student's work, so I just say hats off to her for all the good work she did. So this, all of this is circulation space. Okay, so we modeled circulation space as best we could, given whatever that STORM could or could not do, and these are the locations that we allowed the software to put the 21 different locations. So because the algorithm basically is designed for layout in such a way as to minimize traffic, you can see that given where the operator stands, you have basically put all their points of work in close proximity to what they do. Okay, and that essentially is, so once we have this output, then you basically go back and you say, okay, now can I massage the layout? So what you see here is, I think it's better that you also see what the current state was. So this, we took the operator's routing, and you see all these location points, these were all the location points where we decided to put, there were 21 location points, right? So we took the from to chart and we mapped all those pairwise transitions into this spaghetti diagram. Compare this future state with, this was the current state. So this is how the operator moved in the existing layout of the press area, and this is what we got if we implemented this pseudo approach of using FAST and STORM in combination, basically saying that if the operator is moving between various pairs of points, let's find out all these points, let's see how much movement they make repeatedly between these points, and then try to arrange the workspace and these points around their standing location at the press, and let's see what we can do to minimize the amount of work or the walking work that they have to do. Effectively saying that the less walking you do, there's less fatigue, and especially if you are walking with a heavy load, then you're walking a short distance with a heavy load. So this is the improved workstation layout, and this is the what was there previously. Now, once you have designed the layout, keep in mind again please, we are looking at systems improvement. So not only do we improve the work layout, but we also start asking, could the sequence of execution of the various activities be improved? More so, is it possible that a second person could potentially work in parallel with the main press operator so that the overall cycle time for the entire setup is reduced, right? So this is where the activity scheduling complements the workplace layout. Please go back to what we've been saying about Job Shop Lean, that Job Shop Lean is implemented the same way as you would implement Lean, the Lean thinking process of Womack Jones. Identify value, identify a value stream, change the layout and material flow inside the value stream, then schedule execution inside the value stream. Similarly here, what we are saying is, if you look at a process activity and you're trying to improve, say, setup, you look at it as a process, you change the workspace in which the setup is done, and then you try to improve the scheduling of the various activities. So this is the Tabu search algorithm that we've coded. All that we're doing is solving an operations research problem called resource constrained project scheduling problem. Why? Because there is a resource constraint. You have only so many people available at certain times. And why presence constraint? Because when you do work, certain activities have to be done before other activities can be done. And as in a project where 2 or more activities may need to be done before something can start, similarly in setup, certain activities may need to be done together before something can proceed. And here's what we observed. That when we looked at the various activities, we found that certain activities were predecessors to other activities. So this table may not be very visual. Let me show you what the network looks like. So here's the thing. Sachin sat down with the press operator and they looked at those 236 steps, and the press operator said, oh, you know what, you can group all these elements into a major activity. So these were the major activities that the setup process is comprised of. And then in communication with Sachin, the operator came back and said, you know what, I need to do this before I do this. When I get this done, I can also do this. Okay? Then, for this activity to proceed, both 8 and 7 have to be done. So this is what is called the activity precedence diagram. And if work can be converted into activity elements, and if the activity elements can then be captured in a precedence network, and then for each activity we have a cycle time, and then we have transfer delays between activity locations, we have the makings of a math model for improving work. So much as people might say, well, Lean is about common sense and getting things done, I personally, being an industrial engineer with a reasonable OR background, feel that the next step for us to leapfrog Lean is to say, how can industrial engineering, how can operations research, how can computer science take problems which we today take hours to solve, problems which we cannot solve, if those same problems could be captured in computer form, why then not leverage software that is able to solve those particular problems? Because then we make it possible to solve complicated problems, especially in the job shop where high mix, low volume makes it difficult to take the Lean tools which are great for repetitive work and then adapt them for non-repetitive high mix work. So once you have this representation, of the setup process, you are now in a position to apply scheduling algorithms, and from doing that you can see or find out where it may be possible for a particular operator to maybe help the main press operator. So that's tooling analysis. both layout design and scheduling of work around a constraint machine inside a cell. So at the end of the scheduling, you can see that with one operator, it took about 114 minutes for the setup to execute. When the second operator did certain elements of the setup without violating precedences, it was found that with two people doing the work, the overall setup time could be reduced by almost, I would say, half the time. But what's the challenge here? The challenge is that this person should know when they have to be available to do various work. You see? So when you have a schedule, if you communicate the schedule by phone or electronic display or simply a production meeting, the second person, the water strider, the floater, who is supposed to arrive at this press to help the operator do work in parallel, they can't do it. So again, I may be belaboring a point. It's when people know that they should be doing work where, at what time, the schedule, which is typically ignored in most lean implementations, having the schedule becomes even, how to say, a far more enrichment of work improvement than we would have achieved if we had just stuck with classical thinking like time studies, line balancing, standard work. Not to take anything away from those improvement approaches, but if they were complemented with activity scheduling, we would get even better improvements than what we have gained to this date. So again, the future state design, we had to justify what we had done. So you can see that the big thing was that we pretty much backed all the delay steps between the original process of setup and the new process. And again, we came back and we recorded how much time each of those main setup activities consumed in the new process. And we unfortunately, being academics, we have to prove that anything we propose is worthwhile. So since we had both the processes, and both processes were broken up into certain key activity categories, and each of those categories had a time, we could do a side-by-side comparison of the current state and the future state of the process. So this is essentially, this is the histogram. These are all the major activities, and these bar charts basically are telling you what happened between the current state and the proposed state. And again, when you look at this table, these are the major categories of the industrial engineering decomposition of most work processes, and you can compare 247 steps, operations in the initial process, 235, 32 inspections, 31. Transportation again, naturally, was impacted. Delays were impacted. So, all we did was, true to our industrial engineering roots, we just looked at eliminating what we knew were clearly non-value adding elements in the overall process. So this is just a simple Six Sigma-like statistical analysis, and we basically compared the two processes on each of these categories. So this category, this category, this category. And since the data is not necessarily normally distributed, we ran a non-parametric comparison, and that comparison basically said, you know what, yeah, the new process is improved compared to the previous process. So these were all the recommendations we made. Some of them are common sense. This is where the group technology needs to be applied. It's easy to say standardize, but then to design the tool racks was a capstone project which was undertaken the next quarter. Some of you will probably see elements of 5S, set. This is also kind of a group technology problem. It's part layout design, part group technology. Again, you can see that even in tooling analysis, there are elements of production flow analysis that are common to, say, cell design or factory design. It's just a question of how you use those individual algorithms and, in what sequence you use them. Some more recommendations. This was again, you will recognize that as standard work, absolutely. Checklists. This was important, scheduling. So we don't know if it was implemented, but there was a mention of electronic displays and communication triggers. In fact, on a related topic, there's a side project which we're doing, which is, can we program one of the modern day phones to act as a communication alert system, so that when the ERP system is running and there are hot jobs, to kind of have email alerts sent to the plant manager's phone or the maintenance person's phone. These applications already exist, but I don't know if it's being used in the context of setup preparedness and letting different stakeholders know you are needed for this particular order setup, or to prepare the die for this next order. Some more recommendations, all of this, huddles, production meetings, we know, thanks to Toyota, that let's have people talk. All the people involved in setup, all the people involved in maintenance, just have them talk to each other, and voila, good things will happen. Simple ideas for a small stool. The business case analysis, again, all that we were trying to say was just project that if this is the capacity that you have available, but which you're wasting, if this capacity now becomes available, even if you did X number of setups for different orders, meaning that you did not have one massive run of a particular part. The good thing is that with this time you have saved, that you've released, that same time can be devoted to setup time for extra orders, but then there'll still be leftover time for you to run those orders. And when you fulfill more orders, you make money. Hirschvogel is a premier forging supplier. They know how to use the capacity which they gained back from this project. And if you are familiar with Goldratt, what we did was essentially exploit the constraints. So if you have this much capacity, how can you get back that capacity which today you're wasting in setup? So you can take these numbers with a pinch of salt. Again, the idea again is that it is possible for you to take the improvements of the setup project, and if you can say, well, the value stream will flow from the press, then pretty much what the press will do, you can sell, then this is where the bang for the buck would come about. These are some graphs we used to approximate. So here what we said was that if we perform so many setups, then here's how the available capacity would reduce. That means if you gained or freed up so much capacity, but then you had to make so many setups, then for the time it would take you to perform those many setups, you would eat up some of that freed up capacity. But still, the leftover capacity is what would be available to run parts. So this is just saying that if you did 5 setups and you ran the least profitable part, you would make about so much money. If you basically averaged the earnings from all the parts you make, then if you did 5 setups, this is how much you would make by producing so many parts which were priced at an average value. And again, if you were able to devote all the freed up capacity after 5 setups and you only produce the most profitable part, then this is what you would make. So this is the range of benefits. So as the number of setups increases, of course, you can see that the sales go down, but I'm sure your accountants will know how to figure out the value of capacity gained back due to an application of smart chart process improvement to setup reduction or tooling analysis. This is a quad chart, and much of it is the same data, but the quad chart is something which the Department of Defense expects. And so essentially you've got 4 areas of the screen, and you try and report appropriate important information. Okay, so these are some of the indirect benefits. May not be quantifiable, but I personally believe that a big thing about tooling analysis in setup production is ergonomics and safety. This is where you win the hearts of your employees, especially when you go into risky work areas and apply these improvement methodologies and give those benefits back to your employees. Next steps, again, many steps, but this was actually a capstone project. So, the beauty is that when you work with a university entity, like say Ohio State, yes, some projects you have to pay for. This project was part of a research project, but we're always thinking about what else needs to be done. And so when this thing came up, this project was passed on to a multidisciplinary capstone design project team. and over 2 quarters they delivered uh, a new design for a standardized die rack that was flexible to accommodate different types of dies, and I believe that Hirschvogel actually implemented that die rack design. Uh, this stuff is group technology. I know that Gallagher and Knight have done some work about creating flexible dies by inserts, and just dies of different geometries can be built up by using standard inserts. I'm not the expert on die design, but there are many applications of fast algorithms when it comes to cell reduction, variety reduction, machine design, die standardization. I think depending on a case-by-case basis, I may have ideas. If you asked me how to solve a particular problem, I may have some ideas about how the production flow analysis approach could potentially address part of those problems. This is what Klaus, their internal industrial engineer, really emphasized, that we will implement with the people, with the shop employees, and the people discuss how it will be done, when it will be done. So this was die rack design, and this you can see is that these were some of the issues that they had with the existing dies. This was what was eventually implemented. He's the industrial engineering student. He teamed with, I think, 2 mechanical engineering and 1 electrical engineering student. Or maybe he and just 2 ME students were involved. But this was the CAD drawing. And I believe that Hirschvogel was happy with these results. And once again, Klaus was so instrumental. I mean, when you have a seasoned industrial engineer or manufacturing engineer working with you, it makes up for some of the inexperience and ignorance that we academics and students take to a real world. They saw so much value in what we were doing. So you can see that this is the original operations process chart that Sachin created, and this was the planning board, the layout drawing, lots of good information. Klaus supported our project. He got us a meeting room. Whenever we needed information, he responded to our request, set aside time for weekly meetings, and made sure that everybody else who was involved or impacted by our project actually got to see us. So there was no free lunch. They didn't want to spend money on lunch for us, but for the amount of support they gave us, it's tremendous. I wish that I could have said this about many of the American companies that we have tried to work with or worked with. There was something to be learned here, a lot to be learned. Thank you, Klaus. In fact, he came and presented in my classes. He even presented at our conferences this work, along with Sachin and Alvin, other students. Some photographs of the workplace. So again, in many cases, the Gemba walk, what you see is what you have. So in some cases, when you take these photographs and you make these small observations, we put these pictures in PowerPoint and we put the text, and then we go and we present to our clients and say, gentlemen, we saw this, what do you think? This is what will be benefited or eliminated or impacted if we did a setup project or some other project. So just some more pictures and more comments. This is very famous. It was like, do you want to hang yourself? Yeah, sure, just walk into the press, It'll go around your neck. More pictures. Again, rack placement is arbitrary. In Six Sigma we talk about variance reduction. That's the whole question, that why shouldn't there be standardization? So, 5S, a place for everything in its place, this is it. Why should there be arbitrariness in where a rack is kept? So create a 5S line to position the rack. So when the forklift driver comes in, they know exactly where to drop die racks off. Some more pictures and comments. Operators to bend, ergonomics. So then, when you videotape, you try and start seeing how many times is the operator bending, and that too at uncomfortable angles. So ergonomics has certain guidelines on bending, reaching beyond safe zones of the shoulders and the hips, or the knees. So everywhere, a lot of ergonomics issues were highlighted. Metal shaving, there was another issue of quality. How come in the die prep area, machining chips ended up between the inserts? I mean, when the alignment of the die piece is incorrect, boom, what you get is a broken die, maybe a broken machine, definitely a bad part. So the checklist is very important, covering the dies to prevent chips from entering spaces. That is it. Thank you very much.